And I'll just put the Hamiltonian operator. I mean, not Hamiltonian, but just a regular operator here.
So could you just repeat your question again? It was like, do you expect to have any long integrals? And it was just the probability stuff, right, Dimitri?
It's
Yeah.
probability stuff and also expectation values. So like something like this here.
Do you have like an example problem or something that we could look at maybe?
Sure, I think I got this one. I haven't done it yet, but I will try. Okay, find the average value for R200 for helium plus ion Z equals to 1 electron. Okay. This is a 2s electron, just knowing from its quantum numbers, and they tell you what the radial probability. I mean the wave function for the radial part. So what you're supposed to do is you're supposed to find expectation value. So you do R of 200, and that's gonna be the integral from 0 to infinity, because that's the boundary conditions for the radius, yeah. And you do I'm just gonna write out the terms first. 2, 0. And then that's the operator, which is the which is what you're trying to find here, onto the other wave function. And we have dr of r squared dr, which are the volume elements, and that always must be in the question. That always must be
wait, what was that?
Oh, I was saying r squared dr has to always be here.
Okay.
Okay, so then we simplify those out. So I'm just gonna see 0 to infinity, then that's Z over 2a. It's 3. Then that's so for anything that's p just means r. So you just put 2 minus r and e to the minus r.
Wait, okay. Sorry, what was that?
Oh, the p just means r. That's what I'm just saying.
So p means okay.
Okay, and just see, and you apply it, and you have r, because that's the operator, r times the other wave function. That's 2 minus r.
Oh, what about the e? Oh, okay. Sorry.
Yeah, I'm gonna like put it there too.
Yeah. Sorry.
So what I'm gonna do is I'm gonna put all the constants and name them into like one constant. So for this here times this, I'm gonna just call that variable w, just right here.
So it's w to the third power, right? Then
I just call whatever this is and whatever this is multiplied by each other. I just called it w.
okay.
So yeah, you'll be right. It'll be w is equal to z over 2a to the third power.
Okay.
And then we multiply everything out. So then we have 2 minus r squared, and then e to the negative 2r, which is over r, which is r. Okay, let's see what else I can do from here.
Wait,
oh, what's up?
no, okay.
Oh wait,
yeah,
yeah,
that's right, Marissa. That's right.
r squared's here. I forgot about that. dr.
Wait, where's the r squared dr? Yeah. So when you multiply
I'll just be r cubed. So I'll simplify that. Oh, what's up? You have a question?
oh no, it makes sense. I see what you did.
Okay, so from here, I expand out the polynomial. I don't have to deal with actually, can I just like, let me just see what else I can do here.
You use substitution or something?
You could, but I just want to expand out so it's easier intervals. I think you could do use substitution, but they want you to the integration rule like right here is what they expect you to use, which
Okay.
yeah. So first, let's go with W and let's expand everything out. So it's like 4 minus 2r minus r squared plus r squared. And then that's going to be e minus r times r to the third dr. And then we separate everything into three integrals. Yeah, three integrals. So it's going to be 0 to infinity times 4 e to the negative r times r to the third dr plus, or should I say minus, minus variable 0 to infinity 2r to the fourth, I believe, times e to the negative r. Yeah, okay. And then it's going to be plus 0 to infinity. Okay. Times r to the fifth, e to the minus r. Now I think I simplified everything correctly. So
And you could just use that thing from earlier that it says in the problem that x to the n e to the negative ax is equal to n factorial over a to the n plus 1.
yes, you were totally right. So in this case, yeah, I'll just use that. So whatever n is, so what this is, n is 3, I believe. And that'll be 4 times 3 factorial over n, yeah, n. Oh, since it's 1, so it's gonna be 1. So it's gonna be like 3 factorial, I think. Because it's gonna be in this case, the a here
It's just
is just 1.
-1, right?
Yeah,
So
1 power is
yeah.
so it's gonna be 3 factorial. Hopefully I get everything correct. But okay, that's minus 2 times, and that's 4 factorial. And then that's plus 5 factorial. Oh wait, not 5. Yeah, 5 factorial.
You could just leave it at that. I got the point. I got that. Let me.
I just want to make sure everything's correct. And I would say for just in case my integral doesn't work, put this into an integration calculator and just like solve it. So from here, let's put everything into integration calculator. Or do you know how to use MATLAB?
No. Oh, I wanted to ask. So it's open book, right? This one, is it?
I think, James, it's open book, right?
It is very much open book.
Okay. Are we so are we allowed to use calculators or anything like that?
You're allowed to use calculators. I don't see. Do you mean like
You are definitely allowed to use calculators because that is all calculus. A calculator ain't gonna do much.
Okay.
with this class, it's really more conceptual than it is like, calculating something, except for calculating energy, but that's pretty much it.
Okay.
Yeah.
What else did I have to ask? What about, go ahead.
Oh, sorry, you can continue.
Okay. Let me see if there's a particular problem where it goes into this super long. Yeah. So do. Yeah, for a problem, this is like the probability that the electron is found within a sphere of radius r, where it has this integral that's from like 0 to 2 pi of the I don't think this one's theta, but it's like a circle with a vertical line through it, and then 0 to pi d theta sine theta, and then 0 to r dr r squared, and then the it's kind of like this one, but it has like two parts in front of it.
You mean this here? Like the expectation value?
Yeah.
They're not gonna ask you to do an integral like that. They're gonna ask you to only do just the radial part.
Oh, really?
Yeah, because dude, it would take like so long to do that question.
Yeah, I know. That's why that's why I wanted to know, because I was like, how screwed am I for that question?
If you do, this is like a big if they do, like only just remember just this interval here, but I really don't think they're gonna ask you anything like that. That would be, I think Ranieri would have to be a psychopath. And I went to his office hours before when I was in the class, and he's like not even that, bad. He literally told me what's gonna be on the final. I got a 97 because of that.
I still don't know what I got on my final.
Why don't you ask?
No.
Okay.
The thing is, I have so many questions because I like missed the first exam, and when I looked back and I saw what the exam was like, I was like, holy crap, I should have went. That looked a lot easier than this one, but hopefully they don't try to
Why
go
didn't
too crazy.
And just
Well,
say,
huh?
why did you try to email?
No, it was more like I joined like the class late, and I haven't been really going to the workshops. So like I could do the homework quizzes because I had like more time to like do it, but it was more like me pushing it away and like some like personal stuff. I was stressed. I was just like, you know what? I'm just gonna do what I can to do all right. You know what I mean? Like it was like more like me just pushing it away until I have to deal with it, which is stupid for a class like this, but it is what it is.
Yeah, maybe towards the end you could probably ask.
I really doubt it because I've missed like basically all the workshops. They're just gonna like, maybe if I was like somebody who showed more. I mean, now I'm gonna like do my best, but it's already halfway through the semester, so I don't know.
I mean, if you thought the test was manageable for the first exam, you'll be fine for this exam, as long as you like know the basic stuff. I think you should does he post the quiz answers?
Oh yeah, I've been looking at those.
Yeah, I think based on the quiz, you'll be fine. Because think about it, the amount of time you give him for a quiz is like
Yeah, I know for the test problems, like looking at the last test, the questions were never as long as they are in the workshop. Like the workshop ones are like take like way longer to do.
He doesn't expect you to finish them.
Yeah, I know. Okay, that's a little helpful. Oh,
Oh,
are we okay.
Did you go for our the last year's exam?
The last what?
Last year's exam?
Did I go over? I'm going to tonight. I think he posted the solution, so that'll like help me understand it. Let me take a look at it right now.
You know about rotational energy and stuff, right? Because that's definitely going to be on the exam, rotational energy.
Rotational energy. Let me see. Is this in the last in the practice? I mean the like last year's exams or whatever.
Yeah, with the J levels and stuff. Like, if something rotates, it has a rotational energy. Some, like with a diatomic atom.
Oh, hold up. Okay. So there I do have more questions. Okay.
Let's see. think I have notes for that. It's back here. Wait, do I have notes? Oh, I do. Yes, I do. So if you look at this here, J is your rotational. So basically, think of a rigid rotor. It's two atoms connected to each other, and it rotates by the center of mass. Now, when you calculate the J level, I mean the J quantum number just tells you the J energy. So you know how you calculate the energy for a hydrogen atom, right?
Energy for a hydrogen atom, there's a formula, right? The E, 1 second.
Think of it like this. Instead of the energy relying on N, it's relying on J. So you have to plug in J for that first equation for rotational.
Oh, there's like one long problem. Let me see if I can find it. Was it in one of the workshop questions? Workshop 5. Okay, I can't find it now, but you can go ahead.
So basically, you use J to calculate the rotational energy, and it may ask you the difference between two energy levels. In that case, you subtract the equations like twice. So you subtract the equation with the first energy level, and then subtract it with the second energy level. So you plug in, like, let's say J equals 10. So you
Yeah. Oh, I know exactly which problem you're talking about. Could you like pull it up? Because I was trying to work through it, and there was times where it was just like, I don't know what the.
Okay, I think I have. You mean this one? For the exam?
Oh, okay. This is okay.
So
Do you have these notes like posted online somewhere, or?
I'll send it. I'll send it to you. I forgot to send it, but it's literally on my exam review. But I'll send it to you.
Dimitri, if
Okay.
you have them in a PDF, you can just drop them in the group me.
Oh, I'm not in the group me.
Okay.
Maybe I should be, but
Yes, you should.
Wait, so let me share this link. Let me share this link first. I actually take long, never mind. Okay. So think of it like this here. So rotational is basically the rotational energy. So you calculate, it's asking you to calculate the difference between energy level 10 and 6. So where's the highlighting? So then you plug in whatever 10 is with that first equation.
uh-huh.
And then you subtract it by this. And since you're subtracting these and B is the same, you simplify B out. Does that make sense?
Yeah, you could just factor the B, yeah.
Okay, I just wanted to make sure. Okay, and B is the rotational constant, and B is equal to this here.
Yeah, okay.
And B is in units of energy. So the units of the energy is dependent on the units of B. I just dropped something. And so basically B determines your energy. So you don't have to worry about conversion or anything as long as you have B, you know?
Okay.
Okay, so part B is kind of like really like selective like math and stuff. You just have to like think of it like this. You put everything in terms for
Of
this.
the other?
Yes, exactly. So like think of this. Consider the
But I can't really read the problem, but it's saying, is it basically asking to find the mass of the other using a relation of them?
it's basically asking let's see, the energy difference between a new one, so like A and B.
Uh-huh.
Like this is a new molecule, but it's
Okay.
related to the old molecule by this. The old molecule was MB, and this is like 0.85 times the original molecule MB, so of mass
Mhm.
B. and this is for mass A2.
So can't you just factor out that 0.85 and it's just 0.85 times what the originals? No, wait, that's not how it works because there's a plus
You're,
and there's
you're on the right track. You're on the right track. It's kind of like this. So B is equal to this,
yeah.
and then the reduced, you have to calculate the reduced mass. And the new reduced mass here is related to this equation. And then you simplify it. You put, you plug in what MA and MB are, and then you simplify this out, which
Wait,
is,
do you know what the original, you don't know what the original MA and MB are, right? So
no. Mhm.
uh
It's,
so sorry to cut you off, but you would factor 0.85 squared out of the top and 0.85 out of the bottom, basically, and that's how you get that thing you have there.
yes, exactly. And then after you do that, you pretty much, because we know what B is. So if we simplify everything out, we're gonna have this value and we're gonna multiply it by whatever we factor out.
Okay.
So from here, we know what this is. And then we can simplify, we can put this in terms of 0.85 times the reduced mass.
Mhm.
And this is 0.98313 times the old mass. And then we square that. And then we
The radius, you mean?
yeah, the
Right.
radius. I think yeah. And then from here, I mean it's a bond length.
Bond length, right.
And then we simplify that out. And then we know what B is, right? And then simplify it to this value and we multiply whatever we factored out and we get the new B value. Then you use this new B value to calculate the energy level difference between this one and this one, which is what they asked.
Okay. So ha-
Just ask as many questions for this question for this.
could you scroll up a little bit?
Yeah. Got you.
Uh okay. Oh, I see what so you factored out the 0.85 and the 0.913 squared. You wait. Yeah. No. Hold up.
Yeah, you're on the right track.
Okay. So you basically you multiplied 0.85 by 0.913 by 0.913. And you got 0.708, and then it's 2 mu times the radial length AB squared, and you already have that original value, right?
Yeah, exactly. Yeah. And
Okay.
and that's what I simplified down here. So what I'm basically doing for this is I'm like getting all of the all of these values, right, that are related to the old equation, and
Mhm.
we're going to try to get all of these equal to the original B, which is what our goal is right here, because this is equal to, if you see right here,
Okay, yeah.
this problem is tricky because of that. Because I'm like good at like math and stuff, like I figured it out. And also, yeah, I just figured it out based on that. I think it was kind of like not that great for people, that this question wasn't that great for people, because just had to like know that they thought they had to find what MA and MB are, but
Uh-huh.
it's just relating to the old equation, putting into variables that go back to relate to old B, and then just solve it like that.
Okay, could you, oh wait, so that term that you circled in blue, that's just equal to B?
Yes.
That's the formula we have. Okay.
Yeah, because it
And
has,
then B last time was the 25.52. Okay.
yeah.
But the uh the 0.708, how did that become 1.411?
Oh, it's 1/7, 0.7.
Right. Okay. All right, that makes sense. Um Wait. Oh, hold up. So, mm, but so if dividing by 0.708 or multiplying by 1.411 is bit same thing. Okay.
Yeah, exactly. You
Um,
can write over 0.708, but I just like simplified it because why not?
okay. For the values that we use for like h bar or h bar squared,
Mhm.
sometimes in the problems we would use it with like let me see what units I have for it. Like, I don't know if this is the right way to say it, but erg seconds, like ERG seconds,
Yeah.
or
Mhm.
so is that the one we use, or joules seconds? Because one of them is the other to the
Um,
factor 10 to the 7.
so it depends. Okay, so ergs per second is
Is for
like
is when you have centimeters.
I think it's centimeters. Yeah, I
Because
think
it makes sense for joules that you would have meters.
so. Yeah, it's like I think it's for CGI units. So if it was ergs per second, reduced mass would be in grams, and I think yeah, radius would be in centimeters. If it was SI units, h bar square will be in joules per second, and mu would be kilograms, and the radius would be in meters. You're just thinking like in terms of physics and stuff, but yeah. And I don't think they're gonna like tell you like they're probably gonna give you what B is, and then you just do the question. Because doing all that stuff in units and stuff is like too much.
Yeah, it's 55 minutes, right? So
Yeah.
there's gonna be no way to ask 5 questions and they all like do that kind of thing.
Yeah, that's why whenever if you have to calculate the energy of a hydrogen atom, put it, if they don't tell you what units to put it in Hartrees, because Hartrees is like the easiest units to put in. And if they tell you, oh, it gave you -5 because like, oh, you put it in Hartrees, but just say, listen, you didn't say what unit to put it in. That's what you have to say.
Okay.
Like some questions, like I think the first question asked you to put in like I think they implied to put in electron volts, but they didn't ever ask you to put in electron volts. So that's why I say abuse the system. Like definitely abuse the system with that.
Okay. Okay.
You know what heart trees are, right?
Hartree, I wrote it somewhere. It's like equal to, where is it?
It's basically when you write in the energy equation, it's z squared over 2n squared, and whatever you calculate, that's in heart trees.
Okay,
They
could you say that one more time? Hartree.
Yes, I can pull it up
So
actually.
z squared over what?
Z squared over 2n squared. And I have it in my notes here. Yeah, right here. This is Hartrees' below. And
Okay. Oh, is it negative?
it's negative because yeah, negative. And for hydrogen atom, energy is always negative.
Okay.
For ionization potential, it's always positive. Because
Yeah,
ionization,
it's just equal to negative EN.
yeah, got it.
If you would want to find the difference between two ionizing potentials, then it would just be EN of one of them minus EN of the other.
Yes. If you can't tell the difference between two ionization potentials because they're both positive. So you can just subtract them.
Okay. Oh, somebody else had a question.
Oh wait, there's people here? I did not-
Yeah,
Okay.
I just saw too.
Let us see. Let us see. Excuse me, can I ask a question after? You can ask a question right now.
Okay, excuse me. So I just have a question about the quantum numbers where we're solving the I think it's problem 5 on the 2021. Yeah, about that. So when we have like N, M, L, and spin, are those numbers are the same, then it's called normalized and it equals to 1, right?
Yes.
Okay, when like any one of them doesn't match, it calls orthogonal and equals to 0, right?
Yes, and yeah, because that relates to two different eigenvalues. Yeah, that's because they're orthogonal.
Okay, okay, thank you. And about the well, the wave function, we have spatial and spin. I don't actually understand like that part where we have symmetric and anti-symmetric.
Yes, I will talk to you. You just want to go over a question, right? Like,
Yeah,
so anti-symmetry and symmetry just mean that the electrons, so it just means when you interchange them in space, the wave function can either be the same or it can be negative. Does that make sense?
I think so.
Okay, I'll show you an example. So let's say for this one, for part D is a good example. So this is called, I forgot what the operator is called, but pretty much when you this operator interchange them between space. And I'll show you this example here. Where is it? I didn't like interchange them. But where, I think I put the example somewhere. Okay, so I'll just like write it down real quick. So if you were to interchange this between space, this will equal to the same wave function. This is equal to the same wave function. But if you were to interchange the one below, so if you were to apply this operator onto this, 1, 2, then this would be negative 1, 2.
Okay, so the spatial one doesn't change, but the spin one change when
Yeah.
you do that.
And that's because of this here. If this was minus, this would be anti-symmetric.
Can you see that again?
If this was minus, this would be anti-symmetric.
Oh, let me see.
And for I think an electron wave function must be anti-symmetric because fermions are anti-symmetric. So if the spatial part is if the spatial part is symmetric and the spin part is anti-symmetric, that means the overall wave function is anti-symmetric, which is what we want. Does that make sense?
Yes, I know that. I just don't know, like sometimes it'll be just 1s1, 1s2, and then sometimes it'll just be like 1s1, 1s1.
Okay, so I'll explain to you that. Your professor talked to you about Slater determinants?
I don't know.
Okay, so he didn't teach you about that. Okay, so how Slater determinants tell you what the electron orientation will be. It involves matrices, but I think you learn it later on. But how I remember this is since they're not going to ask you anything like 3 electrons, I'll just teach you this trick. So, like, okay, I know I wrote it down like somewhere. Give me 1 second. I need to pull it. I had this question again before. Let me just if it's here. Okay. All right. So when you have, let's say for part C, you're gonna have both electrons in the 1s orbital. Now we don't know which electron, we don't know if electron 1 is spin up and electron 2 is spin down. So we have to put those both probabilities and multiply them by each other. So for the spatial part, we have 1s1 times 1s2. Because they're both in the 1s orbital, they're gonna have only one term with their spatial part. Does that make sense?
Okay.
Now, because they're opposite spins, they're gonna have 2 terms because you're gonna have to deal with, so one, it can either electron 1 can be spin up but it can also be spin down. And electron 2 can be spin down, but it can also be spin 1. So they both put this probability. So this first term represents if electron 1 is spin up and electron 2 is spin down. And the second term represents if electron 1 is spin up and electron 2 is spin down.
Okay.
That's because alpha, you know how alpha and beta relate to spins, right?
Yeah.
Okay, so that's why we put those two terms. And let's go on to the next part. So let's say that they want the spin to be anti-symmetric. So we know we just have to put a minus sign, right?
Mm,
So we just have the original, we just put a minus sign. Now, the spatial part is different because they're in two orbitals, but we're not explicitly, it doesn't explicitly say if it's spin up or, wait, not spin up. We don't explicitly know which electron is 1 or 2. We don't know if electron 1's in the 1s orbital or electron 2 is in the 2s orbital, right? Because they're interchangeable. We can call it either one. Give me 1 second. Wait, where is it? Sorry about that. But
okay.
we just put both of these terms to account for these probabilities because these are two different orbitals. If they're both in the same orbital, we just have one term here. Now, does that make sense? Do you have any questions about that?
Okay. So the way that we show two possibility is just adding them together.
Yes, because each term represents, oh, we're gonna say this electron 1 is in the 1s orbital, and we're gonna say electron 2 is in the 2s orbital. And then we're gonna add another probability, possibility. Okay, electron 2 is now in the 1s orbital, and electron 1 is in the 2s orbital.
Okay.
Make sense?
Yeah. Can you go back to last one, the last page?
Yeah.
Okay. So that's where you have a plus sign because because it's symmetric.
Yes. Yeah, plus sign because it's symmetric. So they in the first question in part C, so they're asking for a zero order wave function, and they don't explicitly say which is anti-symmetric and symmetric. So a zero order is I think symmetric, but if they tell you the symmetry in the next part, then you have to match the symmetry. Does that make sense?
Zero order means symmetric, and
Okay, zero order means symmetric, but it also they don't tell you what the symmetry is. So that's for part C. This question's weird for part C. Part D,
Oh.
part D is straightforward, but if it's
yeah.
symmetry for either one, then if they don't tell you the symmetry for either one, then just assume it's symmetric. If they also ask in the test, okay, they don't tell me what the symmetry is. They say, what is the symmetry for this? Like, and they tell you the overall wave function is symmetric, then you're gonna probably have, okay, wave function, the spatial part is gonna be symmetric, and the other is gonna be anti-symmetric.
That's what D says.
Yes, that's what D says. And if part C, they tell you that the overall wave function is anti-symmetric, then now I'm gonna let you answer this. What do you think you're gonna do to make this overall anti-symmetric?
What you just make the spin wave function be anti-symmetric.
Yes, and what would you do from that?
I would apply the operator P12 to it.
Yeah, but you could just straight up just put you could just pretty straight up just put minus.
Oh yeah. Yeah.
I just put that operator just to prove that it is anti-symmetric and symmetric. If you know that it'll be anti-symmetric by just putting it minus, you don't have to put the operator there. It's just to help you prove that it is. Does that make sense?
Okay.
Because I just put that there just to tell, okay, this is what it does. I mean, this is what I made the wave function. and this proves that this is symmetric or anti-symmetric. So you don't have to put,
Okay,
yeah, if you know it's specifically that, then you'll be fine. I'll just apply the operator just for it to make sense.
okay. So we first write out the symmetric one, like you did in line 3, where no, not A, alpha 1, beta 2 plus alpha 2, beta 1, and then we reverse it. Like we do it in alpha 2, beta 1. Wait, that's a plus sign.
Yes, because the operator just proves it's symmetric. I'm not changing anything yet.
Oh,
That's why I'm saying you don't have to, if you notice wave function is going to be symmetric, you don't have to apply the operator. I just did that just to like help you guys understand what this means.
okay. If you want to make it anti-symmetric, it'll just be alpha 2, beta 1 minus alpha 1, beta 2.
Yeah, or you can just put alpha 1 beta 2 or minus alpha 1 beta. You can, either one works.
Okay, okay, thank you.
Yep. You have any more questions?
I think that's it for now. Thank you.
No problem. All right. Anyone else have any other questions?
Yeah.
Oh, is it this question?
I mean, I'm kind of like totally lost on this one. But maybe I gotta look at chapter 7 a little more then.
I can explain it again if you want. It's perfectly fine.
Okay, could you do that? Sorry.
All right. Okay, so basically with symmetry, it's all about what you want the overall wave function is to be. So for fermions, like you want the electronic wave function to be anti-symmetric, but in this case, they don't tell you exactly what they want to do. So let me go on to part D because it's a lot easier. So let's say it wants you to propose a wave function for the one of the lowest energy for beryllium 2 plus, and for you to propose that they specifically say that the space part of the wave function is symmetric and the spin part is anti-symmetric. Now, when you make the wave function, you have to include both probabilities that the one you have coordinate systems of one electron and another electron. Now, when you wait, am I on part D? Yeah, I'll go to the spatial part. Okay, so when you do this, when you do the wave function, you have to also assume that it's possible that the first that we call like the first electron can be in the 1s orbital or in the 2s orbital, and the second electron can be in the 2s orbital or the 1s orbital. Now
Okay.
you put both those probabilities there, and I draw a diagram here just for it to make sense. So let's say our first scenario, the first electron can be in the 1s orbital, and this 2s electron can be in the second electron can be in the 2s orbital. Now that's one probability. That's one possibility here. Now we include another term where the 1s the second electron can be in the 1s orbital, and the electron 1 can be in the 2s orbital, and the second electron can be in the 1s orbital. Okay, we put that here. And they say that this is symmetric, so we put a plus sign here. And this operator here is just to prove it's symmetric. So this operator basically turned 1 into 2 and 2 into 1. And when you do all that stuff, you're going to find that this is the same wave function, it's symmetric. Does that make sense? You want me to go back on anything?
Uh, okay. So the 1 and 2 is corresponding to the 1s and 2s orbitals, but you're choosing 1s and 2s because it's the lowest energy excited state.
Yes.
So if it's the lowest, where exactly are you getting the? Oh, okay. 1s is from what do you call it? The ground state, and then the 2s is from that excited state.
Exactly, yeah. At the excited state, the electron jumps up at energy level. One electron does.
Okay, right. So why then do you still include the one, if that makes sense?
Okay, so we're saying that the one and okay, electron one and electron two. These are okay, electron one, electron two. We're not talking about any energy levels yet, right?
Yeah. I understand. So there's a possibility that the first electron is in the 1s and the second electron is in 2s, and or there's a possibility that the first electron's in 2s and that the second electron is in 1s.
Yes, that's why we put both those possibilities down and we put them into linear combinations.
Okay, all right, that makes sense.
Yeah, that's an easy way to explain it. You can use Slater determinants to determine this, but I would say this is much more straightforward with 2 electrons. For 3 electrons, it gets a little much, but actually it doesn't get a little much if you just think about it rationally. But and you're gonna have like more than 3 terms, I think, or exactly 3 terms. But yeah,
Well, there's how many combinations could you do? That the amount of combinations that you could do it would determine how many terms you have, no?
yes, I think exactly, yeah. Slater, and if you do Slater determinants, it tells you it just does the work for you by just doing that. But it's just like it's just long. Good.
So if it were 3, um,
It's
and
on your test is not going to be 3, but you can continue.
oh, then fuck it, never mind.
Well, you can, I mean, you can still ask if you want, but
What was that?
you can still ask if you want, if you just want to learn. But
I mean, I do want to learn, but
I want to.
not 12 hours before the test.
All right. Do you have any more questions about this at all?
Yeah, so you said now, so the wave function is symmetric, and the spin part is anti-symmetric. So how do you incorporate that now that the spin part is anti-symmetric?
You just put a minus sign between two possibilities. So this time the electron one can be spin up and electron two can be spin down. But we also include just like in the spatial part, we include the other term where electron two can be spin up and electron two can be spin down, which is right here.
So what if the spin part was symmetric? Then there'd be a plus sign?
Yes.
Okay.
Yeah, exactly. And that's why I put the minus sign. And this operator just proves that it turns 1 into 2 and 2 into 1. And then you're gonna find if you do that, it's gonna be the original wave function times -1, which proves it's anti-symmetric. You don't have to write this on the test. This is just to help you understand it. If you know just by memorizing how to do it, you don't have to put these operators in here. It's just to help you like
Remember how to
yeah,
do it?
verify it. Yeah.
Okay. Could you go back to the last to the problem itself, like the whole problem?
Yes. Well, I'm gonna go over this part actually, just in
Okay.
yeah. I'll just tell you if they're both in the let's say they're both in the same orbital, when you write in the first term includes the both probabilities anyway. Because if you write on the other term, it's basically the same thing. Does that make sense for the spatial part? If you put another probability where 1s1 can be 1s2, it's basically the same term. And that's
But
why
here there's no excited state though, no?
no, it's the same, it's a ground state.
Yeah, because if it was excited state, then it'd have to go up to 2s or right?
Yeah.
Okay. Um hmm,
Okay. You want to go to the whole question now? Or you want to
wait, so I'm confused how you would show like work for this.
no, you can just write it down. This much
Oh, you
work.
would just write 1s1, 1s2?
Yeah, you don't even have to write the operators. You can just like do this.
Okay.
Yeah. It's much more conceptual question than anything.
Okay.
What else? So this question I think is a toughie. So right here, you would use the multi-electron operator equation where for part A, they ask you for the Hamiltonian for a 2-electron system for beryllium 2+, and all you need to do is just plug in like if it was Z and everything, but pretty much since it's gonna N is the amount of electrons, and since there's 2 electrons, you're gonna have 2 terms here, and you're gonna have to include 1 and 2 because of the coordinate systems, right?
Okay.
And then you would include this, which is this term, and since beryllium has 4 protons, you're gonna have put the 4 here for Z and the 4 here because it's a +4 for a nucleus.
Oh, if we don't, oh, okay, no, it says it in the, I was gonna say, because if we don't remember that beryllium's atomic number is 4, then, okay. Or, I mean, yeah, it's 4, then we kind of screwed there, but it says it in the problem. Okay.
Okay, and then we include this term. You know what this term is?
That's, so, what exactly does the R correspond to? Is that just the radius to the,
It's the space. It's like the distance between this first and second electron.
that's what R12 is, no?
Yeah, that is, yeah.
Oh, but R1 is just there's distance between the nucleus and the first electron, right?
Yes, exactly.
Okay. So that okay.
And that's the attraction to the nucleus. So these 2 electrons both get attracted to the nucleus, and this is the repulsion from the 2 electrons. Does that make sense?
Oh, okay, that's the repulsion. Okay.
Yeah, and you have to, if you're dealing with this, you have to deal with one interaction because 2 electrons can only interact with themselves once. So you can't count the interaction 2 makes on 1 and 1 makes on 2. You only count the
No,
interaction.
yeah. That's just there's just one interaction there.
Yeah, okay.
Okay.
Now from here, it's asking you to part C, what is it? Equals to 0. Given a difficulty, it's asking for you to 0 or Hamiltonian the reference and include the perturbation. And perturbation is just the other term that's new in the equation. Now, based on, I mean, I already wrote it down, but it's basically since in a 1-electron system, we're referencing a 1-electron system. So that means that
Oh, okay. If I could, so then isn't it just in this case the second term, the 4th term, and the 5th term, or is it just the 5th term?
it's the first, second, third, and 4th term for the reference for this one.
Wait, 1st, 2nd, 3rd, and 4th is the reference?
Yes.
Oh, but you said in a 1-electron system.
Oh, because okay, so this part's kind of confusing, but it's like you deal with 2 references because I don't know how to explain it, but it's think of it like this. It's a 1-electron system, but we're just gonna include all terms that have to deal with a 1-electron system. Because all these terms deal with if the electrons were
Isolated?
yes. So you have to include all these terms here.
Not gonna lie, that doesn't make sense, but sure.
Think of it like this. There's 2 reference systems. That's
Okay.
1, 2.
So basically the perturbation is just the results of their interaction. Like if you were to what do you call? If the reference systems were interacted with each other.
Yes, it's basically okay. So this is the reference system is okay. What if we have 1 electron? You know, I mean the 2 are just 1 electron, but then the perturbation is just like, oh, what's new now? Oh, there's another electron there. What the fuck? But like, yeah, there's another term because of that.
Okay.
Which is this term here. It's basically the term that's like unfamiliar from the reference.
Okay.
Yeah. The only confusing part I have to say would be in regards to the reference, but just be like, just include the first and second electron. Just pick terms that are familiar for the reference, and you should be fine. And then this term is always a perturbation.
Okay. All right. All right.
Does that make much more sense?
Yeah.
Okay.
Okay.
All right.
I don't know if I'm holding you guys up or something, because it's past 8. So sorry about that. If you guys gotta go, gotta go.
It's fine. Anyone got any other last minute questions?
I have one more, just real quick.
Yes. Is it on this question, I'm guessing, or something else?
No, it's not. It's about the energy formula stuff. Can I share my screen?
Yeah.
Everybody is allowed to share the screen.
I can't. Can you quit your screen sharing?
Yeah. Even you can exit me out of it, I think, but yeah, you can go.
When
no,
did,
I
Marissa,
can't
when did you
actually.
learn about determinants?
Huh? Slater term? What?
She's asking if determinants
Yeah,
are on the test.
Marissa, when did you learn determinants?
So about this energy formula, do these the same? Are these the same?
Yes. What's the R term again? It's
It's Rydberg constant, I think.
yeah, they're both the same.
Okay.
Yeah.
Should I just use this one?
Okay, so I'll teach you like a trick real quick. So if they don't ask you anything about units, okay, it's okay, James. You can use those equations, but let me just teach you something easier. You know what hard trees are, right?
Yeah.
So if they don't tell you specifically what the units are, just use z squared over, I think that's 2n. Put a 2 like next to the n.
Let me see. Hard tree. Well, hard tree don't be
It would be z
like
squared.
z
Yeah.
squared over 2n squared. Okay.
Yeah. If they don't specifically say the units, just use that equation and then just put it in hard trees.
Okay. What if they do say it? What like a value should I use for this electron charge?
Electron charge is in coulombs.
Coulombs.
Yes, but you can use Rydberg's constant.
Okay, so I just completely forget about this.
Yeah, because Rydberg's constant deals with everything in there. Just use whatever equations like required for that thing. Yeah, to tell you it's in joules and stuff. Yeah. They can
Okay.
and they can
I
also
got it.
okay. And one more thing, they can also give you something like, okay, this electron in this system has like this much energy, and you can solve whatever constants in there based on that. You know, does that make sense? You're basically solving for R whatever units they give you.
Okay. Can I just use this unit at the end?
Yeah, but yeah, it depends on what units they ask. But I would say if they don't ask you for any units, specific units, just put your hard trees, you know?
Okay. Okay, I see it. So I don't need to like convert it to EV or anything.
Yeah, unless they ask you, unless they explicitly ask you. And the funny part is, for the first question in my last exam, they don't even ask you an electron volt. They just tell you, oh, this is equal to this and this is equal to this, and they assume to put in electron volts. But if they don't ask you, just put it in hard trees. And if they argue about grading and stuff, just say that you didn't tell me not to put in hard trees. So
Yeah, that makes sense.
okay, and also let me just give you, wait, give me 1 second. I'm going to give you, they most likely might tell you it's in hard trees. If they do, okay. Okay, so if they ask you in hard trees, this is what it's equal to. So write down it's equal to negative 27.211, and then put parentheses z squared over 2n squared.
Term squared? Like
Yeah,
that?
2n,
Oh, 2n, okay.
and that's in electron volts.
Oh, cool.
And I think you should be fine. If they do give you, I think they will give you Rebert constant or whatever. And if they do, you'll be fine.
Yeah, I have it on my notes, so that should be fine.
Yep. It should
Okay.
be.
Okay, thank you. Thank you so much.
Sorry I couldn't help you out before. I know you emailed me before. But
Oh, that's okay. I went to like Caitlin's office hour at the same time that like I asked you. So that's not a problem.
okay. Good luck on the exam.
Thank you.
Oh, I had one last question, if that's okay.
Yeah, go for it.
Well, this is not really pertaining to the material, but any notes that we want to use, does it have to be like printed out or written out, or could we access it from like iPad or a phone or something?
James, you know. So when are you gonna print out your notes?
Well, I have most of them written out.
Okay, so
You can use your iPad actually. I used mine last time. Yeah.
okay.
What about phone? Is phone sus? Is it like they're gonna like not
Phone is sus.
phone is sus? Okay.
I would say like use like go on Gmail, email him and see if you can use your laptop and just say you'll have it off. Maybe phone if you have an airplane mode. That's maybe.
Oh, okay. Okay. I understand.
Better to have your laptop, you know.
Yeah.
Have a PDFs and just email ahead of time saying, "Oh, can I use my laptop? Because I literally have all my notes on here. Please, like, help me out." Email Sears first.
Okay.
Yeah.
Uh,
I don't think it's gonna fold for that. Serious understanding. That's what I did for my quantum exam. Not this class, but the next level. And he said yes every time. But yeah. I know I said last question, but Marissa, do you have any questions? Because everybody asked a question,
I kind of just came here because I lost hope, and the book notes are making me die inside. I have nothing.
You'll do fine. I think it won't be that hard. Also, I think Mohammed, you're on the group chat, right?
the group me now.
Okay.
I sent an email
You sent the email.
Okay.
so many times.
I will send my notes that I put in the video.
Okay. Cool.
And Marissa, I would say go over, if you're last minute studying, go over the quizzes and the solutions, and you might be fine. Because it's probably looking like that he's gonna like base it on the quiz. Because I looked at the quizzes and they were short enough to be yeah, you're
Test
welcome.
questions.
Yeah, like he might make them shorter. I mean, don't quote me on that. But yeah.
When you say quiz questions, you mean like the workshop quizzes or homework quiz questions or?
Workshop quizzes.
Oh, okay.
Go over those workshop quizzes and I will post my notes. Don't use my notes as like 100% fact. I would say read my notes alongside with going over the lecture notes. But
I really just hope the problems are not like the recitation problems, because recitation problems.
if it was, I think I would actually, that would be too much,
Yeah. What it wasn't. I mean, the last test had one question that was kind of like one from the recitation, but that was it.
I think the only thing he might ask that's probably on the test is probability of finding an electron at this radius, but that's like a big if. And
That's the long integral thing, right? Where two of them are already like normalized.
oh no, it's the question where you have to take derivative. He's not. I don't think he's gonna ask you that.
Derivative?
Yes. It's like you know what probability is, right?
It's just the wave, well,
Yeah.
wave function squared, right?
Yeah. Wave function squared times r squared.
Yeah.
You take the derivative of that. Don't integrate at all to take derivative of that. The probability squared times r squared, and then equal to 0 and solve for r. But I don't think he's gonna ask you for that, something like that.
Okay.
But yeah, you should be fine. Join James's link. I will post my notes.
We have a question in the group me saying, they could ask, could they ask anything about polymatrices? Matrices? If they're asking, they haven't seen them in the prior exams. Did you learn about polymatrices like yesterday? Or was that just like somewhere way earlier? To any of the two of you that have gone to lecture.
Oh, I have not gone to lecture either.
Oh my God.
But there was like some matrix stuff at the end of like chapter 7.
It was probably
And probably you will have it on your exam.
oh man, I really don't think he's gonna do that though.
Doesn't he like cut off like the Monday before the exam?
He does. I think that there wasn't there was like stuff on the particle in a box in the last one, but there was nothing like of the more on tunneling. Like I didn't see that, so I'm guessing he doesn't put it.
Funny thing is, he did put tunneling on our first exam, and I fucking failed that question. But I don't think it's gonna be that much because I think for one of them that's include matrices, I just taught you a shorter way of doing it by the by that question. So I think you should be fine. If I hadn't taken that newer quantum class next level, I think I would have actually not known all this stuff because it very much reinforced everything. I have never in my life completed a matrix. So you'll be fine. Don't worry. If he asks you about matrices, I don't know. Like,
Just think about it. If you know how to do half of everything, then you're fine.
yeah, just swing it.
The average was like a 54 last time. If it keeps dropping, it's fine.
Wasn't that hard and hard?
Does he curve it in any way? Or
Yes, super hard.
Wait, really?
Yeah.
Someone got a 40 and got a C plus in that class. So.
Yep.
Oh, but well, I mean, maybe my hopes are gone a little bit, but is an A still like an 85, or if like everybody does
Yes,
shit,
an A 85 is well above an A requirement.
I think he also said I think he lowered down the threshold for our class. I think like an 83 maybe or 80 is that A?
He definitely lowered it a lot.
If he gives you a math lab question, I think he's gonna give us the math lab question if people are doing that bad.
Dude, they're like replacing MATLAB in the future. Why would anybody learn MATLAB?
MATLAB is easy, man.
I hate MATLAB.
What is MATLAB? Isn't it like a
don't worry about it.
okay, cool.
It's a programming language.
Huh?
Like are you talking
Like
about MATLAB?
Python. Yes, it's like Python.
Oh no.
Don't worry about it. Don't worry about it. It's like zero. It got zero to do with anything.
Well, it does
Okay.
have a couple problem.
With like 2.
He doesn't give. Oh yeah.
He never gave the extra credit.
He never. Wait, he didn't.
He never gave the extra credit for doing the MATLAB problem.
What the?
Dude, nobody saw that shit.
But oh shit. Well, guys, good luck on your exam. I think you'll be fine.
You get look, Dimitri. There's at the beginning. There's a message for you
Wait, ungrip me or what?
in the chat.
It's a lot of work.
Is in the beginning, which one?
I literally at Dimitri.
Okay, cool.
You said group me.
No, I said the chat, the Zoom chat.
Zoom chat and determinants. At Dimitri. What the? It's from you, James.
I know it is for me.
Oh my gosh, man.
You have to do it like 2 bits. You can make, like, six. Those are the type of problems.
I am gonna sleep with like the biggest anger right now.
It's the third one in a row.
Are you gonna do that at the party? I think.
All right,
I will do it. I'll send it to
Thank
Chris.
you guys. I appreciate all the help.
Yeah, no problem.
Are you gonna send this recording out?
Yes, I am. I've been recording it for a reason.
Okay,
Actually, I'm going to
thank
stop
you.
recording now.